I'll do the slides.
Alrighty, easy. Welcome everybody to our fourth and final building success session. Today we have Lachlan joining us from New Zealand. And so today we're going to go over an introduction to programming. And if you guys have any questions as we go along, feel free to ask in chat and we'll try our best to answer those. We are tackling a bit like some more harder concepts today. So definitely if you get stuck on something, make sure you ask. And we'll also have a bigger Q&A at the end if you guys have any other additional questions that aren't as relevant to what we're currently going over. Also, I've just posted in chat already an attendance form if you guys mind filling that one out. That one's just for students at the university who are a member of the club, and that's just to make sure that we're logging our attendance. So anyway, Lachlan, I'll hand it to you. Do you want to head over to the next slide?
Let me get my keyboard working. There we go.
Cool. So I just wanted to begin by acknowledging that this meeting is being run on the lands owned by the Wurundjeri people, and I'd like to pay my respects to the elders, both past and present. And yeah, I guess we'll continue on. So my name is Spencer, and I've been doing Vex for 6 or 7 years now. And I'm the 2-time Australian national champion. I've won excellence at nationals twice. I've also qualified for worlds twice, and I've won 3 different state championships over the years. So Victoria and ACT, as well as the excellence award at those events. I'm also one of the only people who's driven a robot off of a table at Worlds, which is amongst one of my favorite achievements.
Very good.
And then we have the much more impressive Lachlan. Did you want to introduce yourself?
Yeah, so I competed in Vex through In the Zone and Turning Point, so 2017 to 2019. I was vaguely also since then mentoring people online and a little bit in person, I guess. So yeah, through the 2 seasons I competed, I was 2-time New Zealand national champion. And in the zone, we won excellence, so that should actually be 2018, not 2019. And in 2018, we made division finals and in the zone at Worlds where we lost pylons because they were very good. And now I am a full-time ethical hacker. So I do something very unrelated to Vex, but still cool and techy, I guess. And so that is me. So I guess I shall kick it off. We'll get into the cool, fun technical stuff. So I know that we've got like a mixed audience here. Some people have been doing Vex for ages. Some people might be quite new to Vex. So I'll try and balance this out with not trying to be condescending, but also trying to cover all my bases here. So we'll start off by just discussing what the main components are of the Vex V5 electronic system. You know, the V5 system is the current generation of Vex products. So the first thing that's in our electronic system is the brain. So this is, you know, what does, I guess, the thinking on our robot. So this is where your code runs, all of your devices connect to it, your motors, your sensors, all of that jazz, your radio, which your joystick connects to, and it's sort of the central part of the actual electronics platform. Next, we have the joystick, which funnily enough is, you can, if you've ever seen an Xbox controller, you should understand very well what that is, what that does. That's how you drive your robot during the driver control period of a Vex game. We have here the battery. You'll never guess what it does. Yeah. Well, and this is the vision sensor, which is more or less kind of deprecated now, but it is a very, very simple sort of mini little camera that has some sort of machine learning stuff in it, which I guess can be useful from time to time, but sort of generally regarded as not the best sensor. That is the inertial measurement unit. It's I think Vex call it the inertial sensor. It's a series of gyroscopes and accelerometers, which is useful for knowing how much your robot's turning. So when you're turning on the spot, you can actually measure, cool, I've turned 90 degrees, whatnot, and actually have a measurement of your heading. This is, I'm not familiar with this part of the lineup. Is this the distance sensor?
Yes, it's the new ultrasonic.
The new ultrasonic sensor for telling how far away things are. Yeah. So yeah. Oh yeah, it uses laser ranging.
Yep.
It sends the beam of light reflect, measures distance based on response time. And that is
the
color sensor. Yeah, cool. The color sensor, which you can use for, as the name implies, sensing the color of something in front of it. That is the new rotation sensor, and it's really just sort of, I guess, marketing crap to mean an encoder. So inside there's a little thing that spins around, and it measures how much the shaft in it turns. So you can see sort of in the hole in the middle here, you put a shaft through, or is it there? Yeah, there. You put a shaft, and the shaft spins, and this measures simply how much it's turning. So if you put that on a shaft that your wheels are driven on, you can use that to sense exactly to point something of a degree how much that shaft is actually turned, which is really useful for measuring how far something's traveling, or measuring sort of what angle your lift is at, or something along those lines. Next, we have the radio. This is what connects the brain. The radio plugs into the brain. The radio connects your joystick so you can control your robot. And then we have this is the new generation of potentiometer. Similar to an encoder, it measures angle, but sort of only over a fixed range, but it's very, very accurate. And one of the differences between an encoder and a potentiometer is if you turn your robot off and turn it back on again, the potentiometer still measures the same position, whereas sort of the encoder's relative to when you turn the robot on, sort of always starts at 0. So potentiometer is quite good for if you're trying to very, very accurately measure the angle at which the angle that something is sort of facing. So it's useful for that sort of stuff, for on an arm or a lift or whatnot. We have a motor. So this is the thing that goes burr. This is how you make your robot move, and sort of, I guess, one of the more core components of the Vex Electronics. We've got fancy animation courtesy of Spencer here. So the motor has 3 gearing choices. We've got a 100 RPM sort of gear cartridge that you can sort of put inside the motor. There's a 200 RPM cartridge and a 600 RPM cartridge. And all of those, because they're gear ratios, so the slowest one, the 100 RPM, has the most torque output, and the fastest one has the least torque output. And then the 200 RPM one is somewhere in the middle. So you can go really, really fast, but with not a lot of actual torque or turning force behind it if you go with the green cartridge, and sort of the opposite with the red. Okay, I just pressed on the wrong keyboard. There we go. So we'll dig straight into some actual code to look at how we actually start using these things together, how we're going to take the input from our joystick and turn that into our motors moving. So I will sort of move my laptop forward a bit so you'll get my face nice and close, because I'm sort of typing over here in front of myself on my other computer. Okay, now I'll probably need to change my screen sharing setup to do this. How to zoom? I feel like a boomer. Where do we go? Here we go. Cool. So, well, I'll first start off with some sort of the actual background first on programming a Vex robot. So for programming, there is sort of one main official option from Vex called Vex Code, which is an environment. I believe now it's primarily supports C++ programming. So you write your code. It's very sort of in Vex's own environment. There's lots of documentation as to how to make motors move. There's all sorts of classes and functions. And you can do things like set up threads or tasks to do various things. And another option, which is my preferred option, Vex Code's a lot better than it was, but this is still my preferred option, is a third-party sort of community-built solution called Pros. It's very similar to Vex Code, but in my opinion, it's a bit more intuitive. There's sort of active community support in some of the Discord servers for it. But at the end of the day, some things more or less carry over. It's just sort of some of the syntax differs slightly. So basically, I will sort of start afresh and I'll open my window here. So to start off, I will zoom in a bit. Cool, that should be nice and readable. So to start off, there's currently 3 sort of main options as to how you actually use Pros. So the first one is that there's a built-in editor that it comes with, which is based on Atom, but that sort of became being deprecated now because Atom's kind of a lame code editor. There's just the command line. So for example, you can there we go. You can basically say pros v5, you'd say conductor, and you say like new project, you give it a name. This is all documented pretty well on their website. If you just search for Vex Pros into Google, you'll find it. And then you can sort of go through the process of creating a new project. I just made a brand new project for doing this, just with that exact command. I've sort of put in my Pros project and it made it, and here we are. So when you first make a project, it'll pop open like this. We've got a number of files sort of chilling alongside here. I'll delete that because that's a remnant of something I was doing earlier. So inside here, we're living in sort of C++ land. So there's, within how Pros actually exposes things to you, we've got a few main functions here that are already written. So up here we have, I'll just sort of go over the notable ones. We have a function here called initialize. You can put inside here any code that you want to run when the robot turns on. Inside here, we have a function called disabled. Inside here, you can put any code that you want when the robot gets disabled, sort of between the periods of autonomous and driver control. So maybe if you need to clean something up between those two. And also at the end of the match, this will be run as well. Competition initialize, this happens when the controller detects that it's plugged into the Vex's field control system. So when you're actually at a match, for those who sort of aren't familiar yet, you plug in a cable into your joystick and that connects to a control system which says, hey, you can turn on and run your autonomous routine. Hey, turn off. And then, hey, you can turn on and run driver control. So all that's managed by the sort of the Vex firmware, and sort of Pros exposes to us functions where we put in our code as to what to do when these things occur. So this happens when the competition system initializes. And we have another function here called autonomous. So at the start of every Vex match in high school, there's a 15-second autonomous period. In Vex University, there's a 45-second autonomous period. And right in here is where you put the code that will run during that initial autonomous period. So that's when the robot's entirely controlled by itself. And then finally in here, we have where we put the code that we want to run when we're in driver control mode, which is the vast majority of the match. So we'll sort of step through, this is sort of the example code here, but I'm just sort of going to get rid of this for now, and we'll sort of start from scratch a little bit. So if we look at sort of basic programming idea of how driver control code works, anybody who's done game programming before might be familiar with this. As in games programming, you'll often have what you maybe call your main loop or your main tick loop or something along those lines. So effectively, we're just constantly wanting to, in a loop repeatedly while true, so that effectively means forever, retrieve information from our joystick and use that to control our motors or do whatever we want with our code. So effectively, what's this saying is forever, we're going to do some stuff and then wait 20 milliseconds, and then we're going to go back to the top. So first thing that we want to do, if we're wanting to do a very basic driver control routine, we want to be able to push forward on our sticks, and we want the robot to move forward. So most simple control schemes, what we call tank control, that's where you push forward on the left stick, the left side of the drive goes forward. You push forward on the right stick, the right side of the drive goes forward. So sort of the first thing we want to do is we want to, now I'll try and once again not be too condescending with explaining sort of basic programming concepts, but I'll try and still make sure I'm covering all my bases. The first thing we want to do is we want to grab some information from the joystick, and we're going to store this in a variable. And we could just call this variable perhaps left power, and we'll just make this an integer so we can store sort of a whole number in there. And we'll say over here we've initialized an object called controller, which represents the joystick. And this is called master because it's the master controller, because you can have more than one, but that's our main controller. So we can say that our left power is equal to, and we'll say, where's my fingers, master dot get analog. And there's sort of a bunch of different things you can put in here. So for example, we can do analog left Y, and that represents the left stick. So we're asking it to get the value of the left stick on the joystick on its sort of up and down axes. And then similarly, I'll keep losing track of my fingers on my keyboard. Similarly, we can say right power equals master dot get analog right Y, and that will give us sort of the up and down axes on our right stick. So far, constantly our code is just sort of forever. It's going to grab the values from the joystick and not do anything with it yet, and then it'll sort of loop over. So what we can do now is, let's say that we've got motors plugged into our brain, one on port 1 on the left side of our drive and one on port 2 on the right side of our drive. So effectively, we want to create objects in our code that we can use to control these motors. So to do that here, we've got the example code provided already does this. So the way it works is we're creating a new motor. We're going to call this one left MTR for motor. And then number 1, we're telling it it's plugged into port number 1. Similar, we're creating another motor here called right motor. And then we're telling it that this one's plugged into number 2. And so simply by saying left motor, we can suddenly do a whole bunch of stuff with this. So a simple example here is we can say dot and move. And inside here, we're going to tell it the amount of power we want the motor to move with, which we get from our joystick, left power. And then we'll do the same for the right motor, and then I'll just sort of review what's happening. Right power. And this is enough code right here to make your robot actually move. So if we look at what's happening, every 20 milliseconds over and over, we're going to grab the position of our left joystick, the position of our right joystick, and these will be of the range of -127s all the way down, +127s all the way up. So we grab those, and then similarly, we we've grabbed that data, we've put it into some variables. We did the same for the right side of the joystick. And then we're simply going to tell the motors to move. So left motor dot move. And the dot move function, this takes a value between -127 and +127 similarly, where -127 is full reverse, +127 is full speed ahead. So we simply have this variable of what we grabbed from our joystick, and we're going to run our motors at that power. Does that all make sense? All good? Cool. Any questions? Are we all good? I'll assume silence means good. Cool. So that's sort of 101, how we, oh, Spencer?
I might just want to add one little thing, right?
Yeah.
So I just thought, like, to demonstrate, like, because I have it with me, just to show that the tank, yeah, just like to show the tank drive, right? I can hold this guy without killing myself. When I run the joystick forward on the left, so like if it's just a little bit, you can see the wheels are barely moving. Whereas if you do it all the way, they're accelerating more. So that's just kind of the whole analog thing. Yeah.
Yeah, perfect.
Back to you.
Cool stuff. Yeah, so that's exactly how it works, is you push it forward a little bit. Yeah, our code's continuously trying to read the value and set the motors to the appropriate power that we're trying to move the motors at. So that's what your basic 101, how we make motors move. So another thing is, what if we had a lift? So on the joystick, we have sort of shoulder buttons on the back that we can press sort of with our fingers as we're gripping the joystick. So you might want to say that when you're pushing one of those bumpers, that your lift maybe moves up, and when you press the other one, your lift maybe moves down. So to do that, we could create a new motor, and so we'll call that pros motor. Could call that lift motor. Maybe we've plugged that into port number 3, in which case we do that just like that. And now we can do stuff like I'll just sort of build this out here. Say if we get our master joystick dot get digital, and if, let's say, I think it's R1 is the top button is being pressed, R1, digital R1. If that button is being pressed, because this will return 1 if it's being pressed and 0 if it's not, then we could say lift motor dot move full speed forwards, so moving our lift up. We could say else if get digital, and then we can try getting the other bumper that we want to use to move down. And we'll say if the top one's being pressed, it'll move the lift up. Else, if the bottom one's being pressed, we will tell it to move the lift down. And then otherwise, if no buttons are being pressed at all, we don't want to apply any power to the motors. And so we'll just say dot move 0, which means apply 0 power. I think there's also a dot stop you could do instead, but I like to sort of keep things consistent and sort of move and use numbers where appropriate. So this sort of gives you that level of control. We've got drive back and forth, and we've got move something up and down. And so you can sort of see with here, you could do things if you've got intakes that need to spin. Similarly, if the button's pressed, move the motor full speed, else stop the motor. That's sort of your basic sort of elements of a simple driver control function. A driver control routine to make your robot actually usable and start to, drive it around, test some mechanisms out and all that. So that's the basics of driver control. I will now share this window again. Like magic. Cool. It's the basics of driver control. So we talked about, about telling the motor to move with some amount of power between -127 and +127, but that only sort of scratches the surface of what we can do with a motor, and actually doesn't tell you a lot about what's actually happening. So when it comes to how you can control the Vex motors, the first most simple type of control they have is voltage control. So, a DC motor, it's a little motor, it spins around. You apply 12 volts to it, and that's the maximum power that the Vex motors will go at. So you apply 12 volts to it, and it'll apply full power in one direction. And if you were to switch down the terminals, it would go full power in the other direction. And inside the Vex motors, there's a little circuit that can let you effectively vary the voltage that's being applied to the motor. So I could say, hey, instead of spinning at 12 volts, spin at 6 volts. And that's what our -127 to +127 maps to. So when we say move at -127, it's applying 12 volts to the motor with a specific polarity, which makes it go in reverse. When we say go at +127, it applies it the other way around, which makes the motor spin round in the forward direction. So we can both use that dot move where it's minus 127 to positive 127. There's also a function called move voltage where we specify it in voltage units instead, between minus 1200 millivolts and positive 1200 millivolts. So it's really good for really good stable control. It's quite responsive. It feels quite natural to drive when you're using that sort of mode of control. And it's sort of a good building block to start building more complicated algorithms on top of. But as well as that, the motors also have a built-in velocity control. So inside the motors, the smart motors, there's a little encoder in there, which the motor uses to tell how fast it's turning based on how fast the little disc spins, and it fires. There's a little light beam that gets broken, and it uses that to figure out how fast it's spinning. And so when you can actually tell the motor, hey, I want you to spin at 100 RPM. Because when you're spinning the motor, let's say with 6 volts of power, whilst half power, it's a 200 RPM motor, it will roughly be 100 RPM. External disturbances, battery voltage difference, etc., can mean that the actual speed it spins varies. So the motors have this velocity control where I say, hey, move at 100 RPM. And if I maybe apply a counter force to the motor or put a load on it, it'll try and correct it to make it spin at your target speed. And similarly, if you gave it a push, it would try and pull back. It would go, oh, I don't need to apply as much power now. And it just does its best to maintain that. The only problem with it is that Vex have tuned it to be as multi-purpose as possible so that it works well on as many mechanisms as possible. But it's not always great on every mechanism. You can get weird behavior sometimes when trying to use it. And the other thing is that it's limited to the advertised speed of the motor. So Vex sell their motors like as a 200 RPM cartridge. If you actually apply 12 volts to it and full power, you can actually get more like 220 RPM out of it. But if you're using the velocity control, it limits you to that advertised 200 RPM. And then the final thing that the motors have built in terms of their control is you can say to it, hey, I want you to try and spin 180 degrees from where you currently are, or I want you to spin 720 degrees around from the position you were when you were turned on. And so that's position control. Once again, the little encoder inside the motor is used, and there's a little circuit board in the motor and a little computer there that reads the position it's at, and it tries to correct itself and use that feedback to figure out how to get to the position you've told it to move to. Once again, Vex have done their best to tune it to be quite multi-purpose, but it doesn't always work very, very well, but it's great for a quick and dirty sort of control system that works pretty decently. So those are sort of your 3 main things. You can either tell that just like apply a certain voltage to it blindly, or you can tell it to try and maintain a certain velocity, or you can tell it to try and turn a certain angle. So we'll talk now about how we can actually use this as a building block to do more custom control with our motors. Because to be honest, 90% of Vex programming is just about trying to move your motors in a very specific way. And it's a surprisingly deep rabbit hole, considering at the surface level, that's all you're trying to do. You're trying to spin a motor in a predictable way. Because when we're doing our autonomous routines, we want our robot to drive the exact same distance every time, to turn the exact same angle. And so everything's all about making motors move really, really precisely. You want your lift to go to a precise height and all of that. So the 2 main sort of modes of control that you think about when you're doing your custom motor control is, the first one is what we call feedback control. So, or closed loop control. We sort of hinted at sort of the motors can do this themselves with their smart modes, where it reads values from the sensor like an encoder, and it goes, okay, I'm currently spinning at 80 RPM, but I want to be spinning at 100 RPM. It does its best. You have some sort of algorithm that tries to increase the power so it reaches that target speed, or similarly, you've got maybe a lift that you're trying to get to raise to 85 degrees, but it measures it's only at 70 degrees. You've got some sort of algorithm that's constantly processing that data and goes, okay, I need to get where I want to go, I need to do this, and applies power to the motor. So if the other thing that we have on the other side works completely differently, we have what's called feed forward control, where we might just say, okay, I know the physical characteristics of my robot. I want it to move at 1.2 meters a second. I know that it takes about 7.2 volts to do that, for example, based on maybe some math you've done, or based on sort of trial and error. And the advantage of that is it's really, really smooth. It works, but it's not necessarily going to take into account any disturbances. So if maybe your battery voltage is sort of like a bit low, or you're not getting full current out of your motors, there's a bit more friction on your wheels, or you get a bit more wheels slipping, or your robot bumps into something, worst case scenario, it won't be able to know that it's not hitting its target. So that sort of feedback control gets you that stability of ensuring that you get that accurate hitting of your target. So we'll talk about sort of baby steps as to how we actually get our robot to move autonomously. So sort of the first most simple thing is that, okay, I know my robot moves at 1 meter a second. I want it to drive 2 meters. So I'll turn my motors on for 2 seconds, and then I'll turn my motors off and hope that because, we've taken the distance, divided it by the velocity, I've roughly figured out a time period to get it to drive an amount that I want it to. To be honest, and it works surprisingly well to do something like this. It's sort of, I guess, your baby's first step into making the robot do something by itself. So you could say drive forward for 2 seconds, turn on the spot for half a second, drive forward another 3 seconds, turn, for this amount, so on and so forth to navigate around the field. Only problem is that it's really susceptible to external disturbances and, inconsistencies in the field, different friction, and it's not particularly accurate. But I've got a nifty little simulator that I built, which will hopefully help us actually demonstrate how this works. So I will share a different screen. Give it a second. Cool. So over here, we have my little robot and my little simulation here. Here we have what's called the error. This means how far away is it from its target. So the robot's currently 500 millimeters away from its little target here. Currently monitoring the speed that the motors are going at, which is nothing. The voltage applied, nothing. The current being supplied to the motors, nothing. So if we see what happens if I were to just, this doesn't necessarily perfectly line up with how you'd actually write robot code, but somewhat does. So if I were to say that I want to move my motors at 12 volts, and we'll just let this run and see what happens. Robot goes on, it goes zoom, goes straight past its target, does nothing. So a bit useless there. But if we think about sort of what else we can do, we can say, okay, let's use that idea of moving for a certain period of time. Let's say we move for 12 volts, and then after, this is JavaScript, so this is not quite relevant how you write Vex code, but just for my simulation, let's say we want to then apply 0 volts to the motors after, let's say, a second. See what that happens. The robot goes forward a bit, it slows down, it sort of coasts to a stop. Also, am I correct in saying that my screen share is like 5 seconds behind my talking? Because I've sort of got it in front of me here, and it seems to be a bit behind.
Click it now.
Okay, 3, 2, 1, click.
It's about like half a second off.
Okay, because I've got my laptop in front of me here, and it's like so far behind. Cool. Okay, so this is sort of a nifty little simulation we've got here, where basically we can do something like, okay, imagine this is the real world. We want our robot to hit that target. Okay, so we tried moving it for 1 second, and it's a bit off target. It was like 180 mils shy. Let's try maybe moving it for like 1.5 seconds and sort of see the robot going along. Okay, not quite there. Let's try maybe 1.8 seconds. See how it goes. Oh, so this is sort of a process that, when you're sort of doing your first autonomous routine, this is usually how you actually do it. You do a bit of guess and check with trying to, went past its target a bit there. You do a bit of guess and check with move it for a certain period of time, see if it's about the distance you want it to go. And eventually you'll get something like this where it is more or less getting there. But if I run this multiple times, I've got it configured so that the voltage is a bit randomized to simulate sort of the real world, friction characteristics and stuff like that. So I keep running it over and over. You can see it sort of roughly gets there, but not very consistently. So this is sort of your baby's first step to an autonomous routine. So if we go, okay, how can we improve this? We're sort of flying blind saying, I reckon it will take about 1.6 seconds to get there. Sort of gets there, not very consistently. How can we do better? So let's imagine that on our robot, let me change my share again. Might as well just share the screen, to be honest. There we go. So let's imagine on the robot, on our wheels, we've got an encoder, which is measuring how much the shaft is spinning on the wheels, so that we'll be able to know once we've moved a whole wheel rotation. And let's say that we're trying to, move that same 500 millimeters. There's a little formula that you can use to, just based on the circumference of the wheel, figure out how many degrees turning on the motor relates to how much traveling sort of on the field. So sort of our next sort of step in terms of how we will control our stuff is sort of a very simple feedback controller in terms of we could say, let's go full speed ahead and let's wait until we get to our target and then stop moving. And this is quite a big improvement. We'll see that it's not perfect in a second, but the general idea here, go brr, we hit our target, okay, cut power, and hopefully we stop near our target. If we try and implement this in code, I will get rid of that. So here I've got sort of a loop that runs every so often. So I could say, we'll introduce this concept of sort of error here, which is how far away we are from the target. So I have a little function I made called error equals get error, I believe. And so I could say if error is greater than 0, which means that we are far away from our target, we haven't passed it yet. So if error is greater than 0, I could say move 12 volts, so apply full power to our motors. Else, let's say we've gone past our target, cut power, and hopefully we'll land near our target. And if we run this a couple times, you can sort of see the problem here. It's working a lot more consistently, and it's doing a very similar thing each time, but we're going past our target a little bit. So you can sort of like, I guess, sort of jank it together and make it sort of a little bit more accurate by trying to stop like a before. So you can see I had 28 millimeters of error there, run it again, 29. So this is surprisingly accurate. This is a simulation, so it's a bit more accurate than the real world. But if I were to sort of correct it and say stop when you're, just 29 millimeters away from your target and run it again, I pretty much bang on, I'm stopping on my target. So this is sort of like 101. We can say keep going until you reach near the target and then switch off. Only problem is that this, once again, isn't really going to be the most accurate thing in the world. And my simulation has some sort of random elements to it, but it's not perfectly random. So let's say that we were wanting to move at half speed instead. Let's say we're going to use the exact same algorithm, but we're going to go slower. Are we still going to hit our target? So we're sort of going along quite slowly, but we stop quite short of it. And the reason for that is because it's taken us less time to lose momentum and coast to a stop. So ultimately, the biggest problem in terms of how you control a robot is that at the end of the day, the robot has momentum. And when you cut the power, it will dissipate that momentum over maybe another 30 centimeters of movement, which ultimately means you don't end up where you want to be. And so welcome to the world of more advanced feedback control, where we will start to explore how we can actually solve this problem. And I think I'm sharing the right thing.
Yes.
Yes, cool. You can see the slideshow because It is cool. It is not showing on my laptop in front of me. So okay, there we go. So we're going to introduce a new idea of, so we're thinking about the fact that we're overshooting our target is the technical term when we're sort of just stopping bang on it because we've got our momentum. So what if instead we were to slow down as we approach our target? So let's say we go full speed ahead, but once we're like half a meter away from our target, we'll start slowing down. When we're a quarter of a meter of our target, let's maybe cut the power to half. When we're an eighth of a meter, let's pull the power back even more and slowly decrease the power as we get closer and closer to our target. And a very simple and elegant mathematical way of doing this is we say that we're going to set the voltage of our motors to some miscellaneous value, some miscellaneous constant, which we'll call Kp, and we'll multiply that by how far away we are from our target. So let's say if Kp was equal to 1, maybe, and we're working with our units in meters, that's probably quite a bad value to pick and it wouldn't work very well, but if we were 1 meter away from our target, we'd only be applying a power level of 1 to the motor. When we get half a meter away, we pull that back down to half a power unit and as we get closer and closer, we're trying to slow that down. And if you solve the differential equations for this, you'll find that this results in an exponentially decaying function that hopefully tends to the target. So instead of sort of like going zoom and then just like shooting right past it, we should hopefully curve nice and close to it. So if we look at this in our simulation and see what happens when we sort of implement this formula, come over here. So let's say instead of this, let's say the voltage we'll apply to our motor is equal to, and let's just guess a value, let's say 5 times the error. And we will say, move voltage. So if we are 1 unit away, I think that'll be a millimeter in my world. This is not to scale. Then if we're 1 unit away, then we'll apply 5 volts to the motor. If we were half a unit away, we'd be applying 2.5 volts to the motor. So that's how we're slowing down as we approach our target. This will probably overshoot, or it'll bounce around, because the thing is that what happens here is the whole thing works both ways. If we go in front of our target, it will go, okay, our error is negative error. So because our error is negative, we've gone too far. And then it'll apply negative power to our motors and sort of rein us back a bit. So if we sort of run this a few times, you can see what's happening. We slow down as we get closer. I'll make this value a little bit smaller. So we slow down. I'll make it even smaller still. Let's go for something small like 0.5. 0.5. That's still quite small. Let's go all the way to 0.1. So we're going full speed ahead, and we slow down as we approach our target. So this is sort of the sort of thing that we're interested in, is we're wanting to nice and gradually dissipate our momentum before we even, just kiss our target. Then this is sort of one of the next big upgrades you can do into going from sort of quite simple control to another form of simple control. This is simulation, so it's once again not necessarily super real world. But sort of one disadvantage we've got here is we do crawl right to a stop here. If we're to make it more aggressive by increasing our constant, we'll find that it sort of bounces around because it goes too far, because we've still got a bit of momentum we're struggling to dissipate. If we're to go really, really high and go completely wild, we'll find that it'll probably basically vibrate around our target, because it's sort of like a spring trying to settle. It's effectively, some people refer to a P controller like this as a software-defined spring. So that, it's proportional to how far away you are as sort of the amount of force that you're applying.
Can I just add something quickly, Lachlan?
Yep.
So just as a practical example, like sometimes in competition, if you're using a P control that has a very violent kind of motion as well, when you overshoot the target, if you don't have a good center of balance, the robot can kind of jump a little bit, and then that can change the alignment, which means then when it goes back, it's misaligning everything. So it's important that it isn't super duper bouncy.
So that's sort of the problem we get with P controllers, is they're very good and it's very easy to make something quite accurate. But there's the hard thing to sort of reconcile with is you can make it that it slows down nice and slow as it approaches your target. And then it is beautiful and smooth, but it's not very time efficient. We ideally only want to slow down right at the end. And if you make your P controller more aggressive, then you get a bit bouncy behavior. Wheels might come off the ground, and you start shifting around. And then ultimately, you sort of don't really know where your robot is if it's moving unpredictably. So yeah, so this is sort of like a really good first step for making more accurate control. Simply, once again, we slow nice right down as we approach our target, letting our momentum dissipate. And this is all cool, and it works quite well. And there are many things sort of in the world that work this way. P controllers are used sort of all over sort of control theory. So even, for example, the thing that I showed before, where you just wait till you get to your target, then you cut power. That's how your oven works in your kitchen, is that when you set the target temperature to 200 degrees, it powers it up until it gets close to 200 degrees, and then it turns it off. When it dips back down, as it cools down naturally, it'll turn the heating element back on and off, and on and off. And that's, if you have an electric hob as well, you'll hear it click as the relays click. That's it turning itself on and off to try and sort of maintain, it gets there, cuts power, falls down, gets there, cuts power, turns on. And more advanced temperature control, and your expensive ovens, and like rice cookers, even for their temperature control, can use something like a P controller or something more advanced, which we'll get to in a second. So it's this is just a very, very sort of industry standard, general purpose, simple formula way of reaching a goal with some system where you give it an input and it makes an output. So we will sort of turn up the heat a little bit, and we'll try and deal with this problem of it being either kind of going too far back and having to correct and getting jerky, or just being really slow. So we'll sort of introduce, we talked about this already. We'll define, is it showing my slides? Because it's not sure, I don't see my slides.
Error is target minus position.
Yeah, cool. Because on my laptop, I'm still just seeing my other window. I don't know what that's about. Yeah, so we'll sort of go back. We've got this definition of error is, just to recap, a term of how far we are away from our target. And so if we think about what we talked about before with our P controller, you'll recognize this as we had in our code for the simulation, is that we're setting our voltage to the random sort of number we pick that we just sort of guess and check, I guess. There are ways of finding it sort of in a technical way, but guessing and checking is usually the best way. So we recognize this bit. This is the exact same thing as the P controller. But over here, we have a brand new term here where we have another arbitrary constant here, which we call KD. And we're multiplying this by the rate at which our error is changing. And that sort of sounds a bit arbitrary. There are mathematical sort of derivations of this that show, how this is reached. But effectively what's happening here is we are multiplying something by the derivative of our error will actually equal minus our velocity of our robot. So if our error is decreasing at a rate of 100 millimeters a second, that means our robot is traveling at 100 millimeters a second. Because the error is decreasing at that rate, that means the velocity is positive. So when the derivative of your error is negative, your velocity is positive and vice versa. So what on earth's happening here? Yeah, this looks like a bit arbitrary. What's going on? So the general idea is that when our robot's moving fast, this part is going to be trying to slow it down. Because if our error is increasing rapidly, if our error is decreasing rapidly, we're getting really close really fast to the target. So when we're really closing in, this is going to start actually reducing the power even further. And it might even start applying a negative voltage to the motors to get them to sort of brake as it approaches the target. So it does sound a bit arbitrary, but the general idea is if we're approaching on our target really fast, then the derivative of our error will be quite a big negative number. So we're trying to sort of push on the brakes a little bit as we approach our target. It's kind of similar to driving, I guess, in a way that if you're going too fast, you hit on the brakes, and you're trying to maintain there's a lot of analogies there. I won't sort of ramble on too much. So let's actually look at what this looks like in practice. So a more practical formula is to keep track of the rate at which our error is changing. Then we need to keep track of our error right now as we're doing our calculation in our loop, and the error the last time that we checked it. And by minusing one from the other, we get our change in error. If we're wanting to be very formal about this, we would divide that by our change in time. But because we're picking an arbitrary constant here, we kind of ignore that. So let's look at what actually happens in code here. Let's get our hands dirty. So we've got our P controller here. Sort of look at how this works again. It gets there, but it slows right down. And if we wanted to make it more aggressive, the problem is that it bounces around a bunch, because we want to sort of pull back on the throttle as we approach there, because we're like, we're approaching quite quickly, want to pull back on the throttle. So what we need to do is first, I'm going to keep a variable outside my loop called last error. Set that to 0, which will cause a weird jump at the start, but that's okay. And I'm going to save in that variable at the end of every loop the error there. So what we've got for ourselves here is we can calculate the change in our error. Change in error, which will also be sort of DE if you're sort of doing it notation wise, is going to be equal to our error minus our last error. So if every loop we're getting 5 millimeters closer, then this is going to be equal to 5. And then, but sort of formally, KD would be a negative. Okay, we'll get to that when it comes to it. So let's say we'll choose a random number. So this is sort of that component we talked about earlier, which is this component here. We're going to pick this random number to put in. So let's pick 2 and see what happens. Say 2 times change in error. Now this is going to do something a wee bit funky. Oh no, this should work, I think. Let's try messing around with this number, see what sort of interesting behavior we can get. Oh, that's looking sort of interesting. So you can sort of see that we're pulling back on the throttle as we approach our target there. Let's try increasing this number even more. So we're moving there quite quickly, but that's starting to look pretty slick now. So as we're approaching our target, we're starting to really pull back on that throttle. So we're moving there quite quickly initially, but this number is going to be starting to get quite, it's going to be quite a large negative number as we're going quite quickly. So that's pulling on the brakes. Effectively, it's constantly trying to slow the robot down. And if we're to try and sort of tighten this up even more, let's try a really big number, see what happens. It'll eventually start vibrating, or it'll start doing really funky stuff with moving quite slowly. But this is what we call a PD controller, where we have one term, our proportional term, where we have some number times the error, and we have a derivative term, where we have some number times the change in our error. Specifically, formally, it would be the change in our error over time, but we sort of ignore the over time bit. And if we're to mess with this more, we could maybe, now that we don't have that problem of jumping around at the end, maybe we could make it more aggressive. We could increase these numbers to get there faster. That's starting to look maybe a bit too aggressive, but we can what we'd call dampen it by adding more to our KD term. And we're starting to sort of really tightly close in our target quite quickly there. So this is sort of the process of tuning a PD loop, is that, you know, you've got your robot in front of you, you're just going to be tweaking these random numbers. You first start with no D, just the P. You're trying to find a number that gets it sort of close to the target, maybe goes a bit too far, maybe shakes around a little bit. And then slowly but surely you add in this KD number, which will sort of pull back on the reins as we get there. So that's starting to look really slick now. So if we're to try changing this number to 0 and look at what this P controller would look like without our derivative term, it's all disgusting and bad. So that's really important that we put our dampener in there to make things nice and smooth and chill. All makes sense? All good? Any questions? All good? Cool, cool. All right. So this is sort of our, you know, baby steps into doing more and more. So in this case, actually, I'll run it again. If you look at the voltage, you should see the voltage actually goes into a negative number before it even approaches the target. So, you know, what effectively is happening there is because it sees it's getting really close to the target, is it's going to actually start putting sort of a negative voltage on it to try and apply a torque in the opposite direction to create sort of almost a brake to create more resistance in the motors. So that's sort of like, I guess, more intuition into what's actually happening when you add the derivative term, is it's creating a negative torque, you know, opposing, you know, the motion towards the target to help us be nice and time efficient with getting there fast. So that's sort of your brief sort of how to get from moving, you know, if we think about where we started with move for 1.5 seconds, hope it roughly gets there, to we can, you know, add P control. We're like, okay, we'll slow down there, but either gets shaky or, you know, it's too slow. Then we can make it more aggressive, but we add this dampening term called with the derivative, which helps us pull back on the throttle as we approach on the target even further. So that's our basics of feedback control of your, and that will get you really far and get you to some pretty accurate autonomous routines. So you can use that formula both for driving in a straight line where your distance is measured by an encoder, or if you're turning on the spot where your angle is measured by a gyroscope. But there's a whole bunch of other parts of control theory, and we'll touch briefly on something called motion profiling. I'm not going to go too in depth here, and I'm not going to do an example because the examples are kind of lame in a simulator. This is sort of, I guess, extra for experts in a way. But so all of this relies on sheerly thinking about treating it like a dumb box where we get some input, which is where we are, and we're trying to arbitrarily use some formulas that do work quite well to say, okay, we're this far away, let's apply this much power to the motors. So we're still working a bit arbitrary, not really thinking about what is our robot physically capable of. And if we think about sort of the problems that we get with this sort of approach, is, for example, when you first start moving your robot, your wheels are going to very quickly engage and very quickly start moving forward, and your wheels can actually slip against the ground. And that's not very efficient because, number one, you're losing traction and not actually moving. And number two, it can mean that you can lose track of where you actually are in the field. So there's different ways of doing that. Like you can take a P loop and you can add extra things that you know, ramp up your motor power instead of going straight there. And those can help, but there's other ways we can start thinking about the motion of our robot. So if we think about the characteristics of our robot that we're moving it from point A to point B, if we think about, you know, what are our physical limitations? Okay, well, the robot has a top speed. You know, that's sort of, I guess, a simple thing that we're sort of mindful of. So there's, you know, some limit to how fast we can actually travel. Our robot has, based on how many motors are on it, based on the inertia of the robot, based on its mass, it has, a certain maximum acceleration. So it takes time from your robot doesn't instantly go from not moving to full speed ahead. It takes some amount of time to get there. So our robots have some maximum rate at which they can accelerate. So when we consider this information, we can think of, well, if we know what our robot can do, why don't we make a plan to say, of what a feasible move could be for our robot to make. So we could think, okay, if we're thinking about when our robot's actually moving, we will be starting, let's pay attention to this black line here, this black part of the graph. So this is our velocity over time. So when we start off, our velocity is 0. The robot's not moving. We apply full power to the motors. We will gently accelerate up and we will make our way up here. So this is where we max out at our robot's top speed. Notice here this is linear and does assume a constant acceleration, which isn't necessarily true, but it gets us close enough in terms of approximating what our robot's capable of. And then we're going to move along for a while. Where did my mouse cursor go? Cool. We're going to move along for a while at our max speed as we're sort of getting close to the target. And then we're going to slow ourselves down gradually to a stop to when we actually then reach our target. So this is a form of what you'd consider motion planning. We're thinking, what can our motors do? And we're going to create a plan for how to actually do that. And if we look at our position over time, we get a very nice graph of position where this is the blue line here. You can see this dotted line is our target. And over time, we accelerate, we start moving at a constant speed, and we decelerate and hopefully nicely approach our target nice and smoothly there. So motion profiling is, I guess, the field of generating a graph that looks like this to say, okay, I want my motors based on what I know about my robot. I want my motors like at this point in time. I want it moving at a velocity of, about 300, over here, a rate of maybe 550 or something. So we're creating effectively a plan of what our robot could do over time. And we want to make our robot follow this plan because it's a very realistic thing of we're not trying to accelerate too fast at the beginning and lose traction, but we're trying to keep a steady rate to efficiently get to top speed and then efficiently stop once again without trying to overshoot and once again without skidding. I'm not sure if I made, yeah. So there's this brings us back to the topic of feed-forward control, where we're blindly flying. We're not thinking about anything we're doing. We're just going to tell the motors to go at a certain amount of power and pray that we get to our destination. So the first simple example of that was apply full power, wait until we get there, and then apply full power, wait a second or two, then stop, because roughly we know how fast our robot moves. But as we sort of said, sort of the coasting at the end, the friction characteristics makes that really, really sketchy and not very accurate. But this motion profile, because we are instead considering what the robot's physically capable of, we can maybe get more accurate results even when we're flying blind without even considering where we physically are. So we can use a formula like this, where we want our robot to move at a certain speed. That's velocity here. We want our robot to go this fast. And our robot's also accelerating. So, well, we'll forget about acceleration for right now. But if we are imagining we start off with our robot's target velocity is 0, we're going to apply no power. That's how you get 0 velocity. You don't apply power to the motor. And then we will increase it over time in proportion to our desired velocity. So we would probably be looking at, where's my mouse gone? Well, it'd be at maybe 0 volts here and gradually increase to 12 volts up here, maintain our 12 volts and gradually decrease to 0 volts, perfectly in proportion to our velocity graph. And that, if we simply run this formula over time, because we gradually accelerate and gradually decelerate, that'll actually be significantly more accurate than just the turn it on, wait a second, turn it off. But the only problem is, once again, our robot has inertia, it has mass. We need a little bit of help to get it to get to speed. So if you were to, apply 6 volts, eventually your robot would get to half speed, but it would take a bit of time to get there because of its, needs to accelerate. So we add in this little extra term, which helps us get there. So when we're accelerating at, let's say, 2 meters per second, we would maybe add an extra volt to the motor's power to help give it a little boost to sort of track along to reach its target. And then similarly at the end, similarly to how we used our derivative term, we want our velocity, we want to be decelerating. We need to be pulling on the brakes a little bit, because if we just, even if we cut the motor's power here, even if we cut power entirely here, we'd probably slowly coast down. So we need to apply some step on the brakes a little bit because we're trying to decelerate. So this simple formula here you don't need a sensor at all. So you don't, to get decent results, simply based on making a plan of what you want your robot to do over time. If you plan where you want your velocity to look like over time, and you know the acceleration there, that's the slope of the acceleration and deceleration periods, and you apply this formula to calculate a voltage to give to your motors, it'll actually do a pretty decent job out the box of following a plan like this. And then, of course, though, we've got real life disturbances, and we want to correct this. And if something does go wrong, motor's not even working, something something terrible's happened, we're not hitting our target, we do want to have a little bit of extra correction there where we are keeping in mind our robot's actual position. So we can add, sort of similarly to before, where we used a P controller just to do everything, we can add just a little sprinkle of P controller to say, okay, if we're a bit behind, we actually want to boost our power up a little bit more. If we're far ahead, we don't need to worry, and we can reduce our power a little bit. So once again, this is a formula that helps your robot take a plan of a target velocity, target acceleration, and target position, and stick to that plan and sort of try and sort of follow that. So I've got a few examples sort of here as to what some real world results of doing this over time, if you bear with me. So this is a slightly different type of motion profile. This is an S-curve profile. It's not a trapezoid. But if we look at this, yeah, they're actually so close you can't tell which one's the target and which one's the measured velocity. But so this is similar to the trapezoid. This is a plan of what we want our motors to do over time. So the red is the target. Actually, there's a green line behind the red, but the line here, this is the target velocity we want our motor to move at over time. And then here we can see the position we want to eventually reach our goal position up here. And the purple here is the voltage that gets applied to the motor. So this was done in quite a complex model that I made like a year ago, where I'm emulating friction characteristics and all that. And we look at what's happening here. We're slowly increasing the voltage to our motor. We eventually peak, and then we eventually sort of slow down again. We look at sort of other examples. Because I do have an example from a real world system here, which I lost my position here. Where are we? I'll sort of, I guess, blab on a bit while I try and find that. So sort of overall, the idea here is we're sort of we're thinking about the physical characteristics of our motors and what they're physically capable of achieving. And because we already know this information, we don't need to rely on sensors as much to do the vast majority of our actual moving. I do have a video here of something or other. Oh man, I had this bookmarked earlier, but I deleted it, and it was on my other computer, so it's not in my history. Yeah, here's an actual example of motors moving, and this is from a friend of mine, William, who's also in 240p. He sort of had a uni project where he was doing some motion control, and he used a trapezoidal profile here. So this is our motor's target velocity over time. You can see the blue line is our target, and we have our actual measured velocity here in the orange line. So basically, we've generated what we want our motor to do over time, and based on what we know about the motor, we know that if we apply 12 volts, it'll move at 200 RPM. We know that if we apply an extra 5 volts, we'll increase our acceleration by this much. Just using a simple formula where you can basically just guess and check the numbers, you can actually get a pretty good what you'd call tracking the profile pretty well. And ultimately the angle of this moved very nice and smoothly. So that there's a whole sort of very, very deep world here as to what you can do with this. And when you're just moving in a straight line, it doesn't matter sort of as much, to do something like this, but where this really gets powerful is if we're trying to get our robot to move in 2 dimensions. So instead of driving in a straight line, if we say we want our robot to move from this position here to all the way over here, not tracking a straight line, instead making a curved shape, using methods where we can plan what we want our motor to do over time is really the only feasible way of achieving that well. So I should have an example somewhere of the sort of crazy things. I'm not going to go into the maths of how to do this stuff in particular, because it does take a lot of work to figure it out. Take me more than just an hour or two to explain, but where are we? Yeah, cool. I shall open this over here. So we've got an example here of applying the same concept, but using it to generate a plan for the left side of the drive, a plan for the right side of the drive, to eventually sort of move in sort of like a squiggly shape there and do sort of more advanced motion. This is using a library that it took me like 2 years to build sort of in my spare time as a sort of fun project.
Just a quick question from the chat, Lachlan.
Yep.
Sam has asked, do we need to optimize the parameters for different robots?
Yes. So there's sort of not really a one size fits all, based on everything from the robot's mass to just, friction characteristics to its center of gravity. You do need to do some degree of trial and error on your different robots. So especially if you've got one robot that's really heavy, that doesn't have many drive motors, and it goes quite slowly, and it's got a wobbly center of gravity, you'd want to make your control in a way that it moves it quite slow and smooth. Whereas if you have a nice, light, fast robot with a low center of gravity, lots of motor power that goes very fast, then you might be writing more aggressive control to really take advantage of that.
Just want to add on as well, with VexU, we have to have 2 robots instead of just one. So we've got a larger one and a smaller one. So both of those robots, you wouldn't be able to use the same parameters for. You'd have to have separate ones because they're different robots with different functionalities. Correct? Yeah, pretty much.
Yeah. And same thing going from like one lift to another lift or any sort of mechanism. No 2 things behave the same. But one value of doing sort of motion planning like this, where you instead make sort of a target of what your motor should do over time, is it can be easy to sort of translate that. If you just alter some of the parameters to the different robots, to different characteristics, you can get it to do sort of a whole bunch of other stuff. I've got another example here. I think this is the right one. This was a very sort of funky move that you can sort of do something along this line. Sort of really complex autonomous control sort of stuff you can do here. And so this is sort of just a slight sort of taster into how you actually, I guess, sort of the range of different things you can explore with motor control. So sort of today touched on the basics of how to use sensor feedback to go from point A to point B, and sort of some very effective, simple algorithms to do that. And so sort of hopefully some pointers to other things you can do. So for example, if you were interested in calculating trapezoidal profiles, you'll sort of need to look into the math of that yourself. But if you just Google trapezoidal profiles and you look at a graph like this, if you've done high school physics, you should be able to get a piece of paper out, spend a bit of time, work out the kinematic equations for, if you know your maximum velocity, if you know your maximum acceleration, to actually write some math to create a graph like that.
I managed to do it, so that means anyone can do
it. It took nights and nights of pain helping you through it, but we got there.
We got there, didn't we?
We got there in the end, and it did work quite well in the end.
It did. I was really happy with it, and it still works. We can apply that to everything. It's great.
Yeah, and so if you're going for cheap and easy as well, instead of using sort of a formula like this to try and get your robot to follow the profile, you can use that inbuilt velocity control that I talked about earlier, where you say to the motor, just over time, you can ignore the position almost entirely, and just over time you say to the motor, please move at 0 RPM, please move at 10 RPM, please move at 20, 30, 40, etc. Which is how we did it with Spencer for your robot in Power Takeover. Yeah,
I think we might have.
Yeah, back in the day. So yeah, there's sort of if you're comfortable with, maybe you're not so comfortable with certain types of math, but this sort of thing, you if you're looking at this and you think, oh, that's easy peasy. I could figure out the equations to calculate this graph in a heartbeat just based on the target distance, max velocity, max acceleration, then that sort of might be something that's worth exploring. In terms of what's best, there honestly isn't a right answer. It seems different people take different approaches. I guess it depends on what you find intuitive to you as well, and just trial and error, what seems to work best for your robot, what seems to work best for the sort of movements your robot's doing. This is a case of sort of with very minimal tuning, you can get very, very effective results. But sort of as I hinted at, there's a whole world, whole industry, whole field of study around how to make a motor move in the way you want it to. So yeah, definitely a lot of depth there. So yeah, that's the general gist of the surface level look into the ways you make a motor move. But I will go into just a little bit about how you'd actually write this and start to structure your code. I'm cognizant that it's been over an hour now, so I might just aim to try and cover maybe 10 minutes of this, then leave 5 minutes for questions and everything else. That sound good?
Sounds good.
Cool. So for thinking about, we've sort of got these concepts of how we want to move our motors, and we've got sort of concepts as to what we can, what we're sort of capable of. Let's look into the nitty gritty of how you'd actually maybe start thinking about writing some C++ code to effectively do this. Now, everyone has a different opinion as the best way to lay out your code. Everyone does it differently. I'll sort of show how I do it for a small code base. I'd flesh things out a bit more if it was a more complex code base. I'll sort of go over, this is the gist of how I would do it in a simple example. So often on your robots, you've got different mechanisms. You've got your drive base, your lift, your intakes, something, who knows what else. I like to make a folder, and so you can have multiple files to keep your code in. So I'd like to make a folder, and I'd maybe call it subsystems or just systems or mechanisms or something. So here I'll just call it reach round subsystems. And I think about, okay, what's on my robot? Well, maybe I've got a drive base. So maybe I'd create a file that I want to store all the code related to my drive base in here. So I might call that drive.cpp for C++. Maybe I've got a lift, and I'll create something called lift.c++. And we sort of start to think about, okay, how can we sort of effectively separate our code in a manageable way that doesn't make it too complicated, but keeps things nice and accessible. So if we look back in sort of the main file that we started with in the template, the first line here is include main.h. That includes a whole bunch of the stuff that we need for the libraries to work. So that's the first line that we're going to put here. I like to use a C++ feature called namespaces, which sort of separates your code out naturally into sort of different chunks, as it were. So to do that, I would simply write namespace drive. And in here, everything here is sort of nice tucked away in its own little section. So if I was thinking really, really sort of simple but effective and manageable code base, I'd still maybe start working with, let's just say it's a simple 2-motor drive. Normally you have more, and there are libraries that let you easily control multiple motors as if they were just a single motor. I will just sort of keep it nice and simple. I'll say left motor, and let's say that's plugged into port 1. And right motor, maybe plugged into port 2. So maybe I want a function that just lets me drive with a certain power straight forward. So I might say I could do set drive, and I could say I could take voltage in here. So I could have this function where I can just set my drive to go either straight forward or straight back. And I can sort of, I guess, abstract away the behavior here. And I'll do the same for the right motor. So thinking about a manageable code base is when I'm writing that should be voltage, not velocity. When I'm writing code that I want to be easy to write my algorithms on top of, I don't want to be worrying about actually setting the voltage to the motor. I want to start abstracting it away to the idea of set drive. Maybe I'd say set drive power, or I'll just say set power because it's already in the drive namespace. Maybe if we're wanting to also be able to easily create something for turning on the spot, I would have something like set turn power, where a positive number would mean that my left motors go forwards, my right motors go backwards, and negative means the other way around. So I can sort of do turning on the spot. I would lay things out quite similarly, except for this time. Oops, I did not copy all that right. Except for this time, when I'm turning, I guess, positively with my left drive going forwards, I need the right side to move backwards. So I just put a negative sign there. That means that it'll turn that into a negative number. And so if I was thinking, okay, I want to make a nice, easy function for using like a P controller, like I described, for getting, to a target, I might create a function called forward, as in, drive forward. Might have a target distance. I think, okay, well, first off, I need to have a sensor in order to measure my distance. So because that sensor might be on one of my wheels, or one thing that's quite common as well, is you have a free spinning wheel that its only purpose is to track how much your robot's moved, because it's not susceptible to wheel slip. It's not susceptible to sort of, gear play and stuff like that. But let's just sort of say, whatever it is, I do have I'm trying to remember, I've not actually used the rotation sensor. What's it called? Is it just, yeah, rotation. Let's say I have a rotation sensor that is measuring how much my robot's turning, and I will call that encoder. Let's say I've plugged that into port maybe like 10 or something. So let's say I'm wanting to move forward a certain distance. The first thing that I might do if I'm just working very simply based on moving from where I am now, first thing I might want to do is reset my encoder's value to 0. Just reset. I think it's just reset position. I want to set the value to 0 because I'm sort of working in the context of I'm starting at this point and I'm going to do a new movement. If you're starting to make a more complex code base, you might want to try and keep track of any accumulated error. And instead of working on where you are now, you might want to work on some, based on some idea of where you actually are in relation to the field, but that's sort of a more complex sort of topic. So let's say I want to drive forward. I could simply say while my encoder position, so I just say encoder.getPosition is smaller than the distance I'm trying to drive, then I want to do something. So I want to calculate my error. So if I'm just sort of doing a simple P controller, because we might be working with decimal places instead of storing it in integer, I'm going to store it in a floating point number. I'm going to say error equals our target distance. And then I'm going to subtract where we actually are. And then I'm going to define that arbitrary number that lets us choose if it's a really soft movement or if it's nice and aggressive. That number we called KP. I might put this up here just so it's nice and easy to find if I want to change it. Let's just set that to 10. And then simply, I will say that I want to set my drive power to the KP times error. And this is sort of exactly what we looked at before, where continuously we're looking at how far away we are from our target and make our drive motors move at some rate in proportion to how far away we are so that we slow down when we get closer. And the final thing that you want to do is you don't want to run this in an infinite loop that goes really, really quickly and consumes resources because the CPU is trying to do multiple things. There's all these background threads that are running, trying to speak to the competition control and all that stuff. So sort of to be polite, we want to add a delay in our code. 10 milliseconds is sort of the standard because that's how often it's called sleep, isn't it? Tell it's been a while. Is it sleep? Or do I need to say I need to do that. Yeah, there we go. So we want to only update it when we need to. We only get sensor data every 10 milliseconds. So every 10 milliseconds, we're going to look at where we are, compare it to where we want to be, and sort of move in proportion to that. And when we go past our target, we'll stop. So this isn't perfect. It's not making sure that we're sort of settled at our target, but it's something. This will work quite well. But the final thing we want to do is we want to make sure that we're completely stopped. So we're going to turn our motors off by setting a power of 0 to them. And that's sort of a very simple way of just driving forward, as we demonstrated with the P controller. You could add a derivative term like we demonstrated earlier if you'd like. And we could do the exact same thing if we want to turn on the spot. So let's say, as well as drive forward, we could say drive turn. So to know how much we've turned, we need to have you can calculate it based on the difference between an encoder on either side of the drive. But to keep it simple, we'll use the gyroscope, the inertial measurement sensor, the inertial sensor, or whatever Vex call it, which we create or is it just IMU? IMU. We'll call that, I guess we could just call it gyro. let's say it's plugged into port 11. And cool. And then so you would tune your KP differently because it's, different characteristics when you're turning versus going back and forward. In this case, we can just sort of say, maybe we want to specify, very specific angles. So let's allow decimal places in our target angle, say target angle. So we could say now that this won't work entirely as intended. It won't let you turn to a negative number, and it won't let you turn backwards, but keep this simple so it doesn't work entirely, but sort of get the gist. Is we say, we called it gyro. And we'll say get yaw. So the yaw angle is how much you're turning in relation, to the z-axis coming out of the ground. It also lets you get your pitch and roll, which is the angle of your robot facing up and down and sort of side to side. That's not particularly useful in Vex. Maybe you can find something creative with when you're platforming to use that value for. Can't think of anything else really that it would be useful for, but this should be good. So whilst we are not yet at our target angle, and it keeps auto formatting my code because I've not set it up how I want it to be. So while we're not yet at our angle, we're going to continuously look at our target angle, and we'll figure out how far away we are from our target angle. And instead of setting up power moving forward, we'll set a turn power. So you would want to add sort of extra conditions in here to make sure that if you were turning sort of to a negative angle, so if you're turning counterclockwise, it would handle that properly. In this case, it would just immediately fail. But so I'm more sort of trying to demonstrate how you'd lay out your code. So the way that I like to do it is you get these nice and simple functions that sort of make things nice and clear. And if we think about how we'd actually start to put this together, for those of you not familiar with C++, this might seem very strange, but we also need to create what we call a header file up here. We'll lay this out exactly the same as the files in our source directory for the subsystems. And we'll create a drive.hpp. We want to tell it to never include this file more than once at the same time because that leads to errors. So we just say pragma once. And we're going to do something that looks very similar to this. This is effectively telling lets our other code files know what functions are available to them. And so we would write it like this. So we made something called set power. I think we won't need to use set turn power anywhere else for now. So I'll sort of show you how this is written, and then I'll show you how it's used and sort of explain it. So effectively, when we do this, we're what you'd say exposing these functions so that other files in our code base can use them. You don't want to necessarily have everything accessible to all your files because that leads to messy code. So we're trying to be very explicit about, maybe in our driver control, we'll need to set the power, and in our autonomous routine, we'll want to sort of turn forward and move forward and turn back and so forth. And to make sure that our other files can use it, if we go over to our main file, we will need to say include subsystems, and we will include our drive header file. And so this will leave me alone. I need to change my settings to make that work, whatever. So this tells it our main.cpp file. It will let it see all of these functions we've exposed. So I'll be able to come down here and I'll get rid of all this code that manually, makes a motor and sets it. And I can instead, I suppose this is actually kind of useless because it'll only let me move forwards or backwards. But I guess we'll sort of leave that for now. Oh yeah, what I can do is I'll make another function called set power that lets me set different speeds for the left and right. And right voltage, left voltage. We'll make that function available to the rest of our code. So now over here, instead of manually doing like set, motor.move, blah, 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 we can very elegantly say drive, set power, left power, and right power. So this is how I like to lay out my code base so that you're encapsulating all this behavior into sort of like a file that's responsible for that mechanism, so that my drive it's exposing something called set power, which abstracts away all that behavior of actually setting the motors to a given voltage. And if we're thinking about similarly how we can, if we're making our autonomous routine, we would say something like drive forward, and maybe we want to drive forward 2000 encoder units. Maybe we then want to turn, we'd say drive turn, we want to turn 90 degrees, turn to face 90 degrees. Maybe we want to then move forward another 100 units, so just a small little movement. Maybe we want to turn and face 135 degrees now, so an additional 45-degree turn. So this is how I like to lay out my code, so that I'm not doing all of my nitty-gritty algorithms in here. And then I'd eventually, when you're writing more than one autonomous routine, it's nice to create a different file for each one. And then you can do fancy stuff like on the brain, you can use the touch screen so that you press a button and it changes which one's loaded up. But sort of keeping it nice and simple and nice and clean. The way that I like to do it is, have these very simple functions. And similarly for my lift, I'm not going to go into it, but similarly, I'd have functions to, set the power for the lift. Maybe I'd have a P controller that tries to move the lift to a certain height or something along those lines. So that's sort of the gist of how to start to nurture a beautiful code base from the start, instead of just putting, ending up with 1,000 lines of code all in one file. It's nice to start moving things into a file, each responsible for their own systems. If you're into C++ programming and you're sort of, into actually writing, object-oriented programming, you might want to make something that, if you're to do, a P controller or a PD controller, or what we didn't talk about, even more advanced, would be a PID controller. You could create a class that represents all of that complex behavior and reuse that across your different systems and sort of all of that stuff. Cool. So that's sort of more or less the gist of overall laying out a code base. I think that was more or less my final slide, but I'll check through the chat and we'll get to that soon. Cool. For that, we'll be applying simulations, or is it solely based on testing? So applying simulations to your robot is honestly kind of, I wouldn't say useless, but it takes so much time to make an accurate simulation that it's not worth it. But it is worth, if you were doing something like a motion profile, it's worth maybe sitting down with the maths and saying, okay, the maximum voltage is 12 volts, maximum speed my motor moves at is 200 RPM. So if I'm trying to figure out, a number to relate that, then maybe, sit down with a paper and pencil and try and maybe work out a few little things. But full-on simulations at sort of within the Vex hardware isn't really worth it from my experiencing. And that, from my experience, partially because it's so easy to test on Vex hardware. Sort of in bigger scale systems, testing a new control scheme can be a big event, and that's why it's worth, making simulations. But within the context of Vex, it's very, very easy to write some code, upload it, run it, have it happen right in front of you, and sort of easy peasy and sort of cool stuff. All right. Awesome. So I'll move on to this slide, which Spencer made. And do you want to say anything to that?
Yeah, so as we've gone over in every single kind of one of these little sessions is how important having a design process is. And I just wanted to relate everything back to this thing that we were talking about in the last session before, and the first session, which is that using an engineering process, every single component of Vex follows it. Everyone gets involved. You're figuring out what's wrong with the program. Maybe it's, it's doing that little, movement thingy with the P control where it's overshooting, right? How do you fix that? Think of some solutions, test the solutions, measure it, and then keep repeating that. And pretty much every single component always follows these processes. And this is something that you can also apply to your own learning. So it's very important that you follow these design processes, and that you're just taking note that these are really important, because a lot of people tend to overlook them. And just kind of to appreciate that we do follow these, even if we don't normally realize it.
Another thing I'd like to add as well is, what was that? A quote I heard: engineer to your requirements, not an ideology. A lot of, especially in programming, a lot of people, especially if they have a strong programming background, but maybe not robotics experience, they're like, oh, I know how I'm going to do this. They pull it out, they write up, 1,000 lines of C++ to abstract all this stuff in these classes and these complex stuff. And just because they can, and because they feel like that it's cool and the right thing, and it's cool because I can do advanced programming and flex my skills. and then you need to like make an obscure change in the middle of a competition. You're like, sorry, I need to recompile my shared library to make that change, and then I need to actually use my my GitHub actions to do my cloud CI/CD. You and keep things simple as possible to start with. Keep it simple, stupid. And don't just immediately shoot for the moon. If a P controller is all it takes to move your lift accurately, it's a very simple, easy to debug controller. It's not the most advanced thing in the world, but it's resilient, it works, might not be perfect, but maintainability, ease of understanding, time investment, it's all part of the engineering process. And I think it especially applies to programming because so many people, they can do something complicated, and just because they can, they try to, and they end up with a program that doesn't work. Because often as the programmer in a team, from experience, I can say getting hands-on time with the robot can be a very rare occurrence if there's all sorts of different changes being made. And so if you have a nice, simple code base that's easy to change and is got, is likely to have no bugs, or as minimal bugs as possible, that really helps you get that valuable hands-on time with the robot and use it effectively. Whereas if your hands-on time with the robot is a case of you sit down, you run it, and you're like, oh, sorry guys, I've got a race condition. This thread's not starting properly, and my semaphore is not properly being taken by here because I think that there's a problem with the round robin. If that's your response to when you first run your code in an actual robot, you're wasting your time. You want to have confidence your code's nice and simple. You run it, it works, easy peasy.
Yeah, and just to add, one of the great advantages about like having more simple systems like the PKP system and all that is that you can literally you'll have a game starting in like 30 seconds, chuck that cable and upload a new program. You can make quick changes and adjustments if you have to. Like usually you wouldn't want to be in that situation where you're changing it last minute, but
we always are.
We always are, and we can. That's what's good about these. They're very easy to adjust, and especially as Lachlan said, if you have a really good code base, it makes it even easier to do it. So. Yeah. Don't take that for granted.
Yeah, because as much as even the best teams like to imagine that they show up to a competition perfectly prepared with full confidence in your robot, anything that can go wrong will go wrong eventually, and it will happen just before a really important match. And I feel right now I'm saying this in front of Jacob, which is probably a bit of an eek moment because that's happened. Yeah, you were on the receiving end of that in your match against us back in Turning Point Nationals. Everything will go wrong eventually, and being able to quickly recover is important. So,
and also just on that, I remember at Nationals for Tower Takeover, Lachlan, I had it was like a 20-point Auton or something. It was getting like 6 or 7 cubes, right? And every single day back at school, it was working perfectly, 100% accurate. I'd run it 20 times in a row. It would work, right? Day of the competition, you put that on a field, did not work once. Put it on a practice field, and I remember I sent you a video, I recorded it, and it was working fine on the practice field. But the thing is, we could make tweaks to that to try fix it whilst we were there, just because of how simple the code base was. So that's another example, but point is, keep it simple.
Yeah, there's a good meme somewhere of your
it was working yesterday. Yeah, my favorite.
There's a few good memes on that.
Yeah.
Once again, competition preparedness is really important. We're not just sitting around, in our lab where we're actually working on our robots, where we're actually programming. Part of the Vex program experience is sitting there on the practice field. You've got a match in 5 minutes. Your Auton's not working. You've got 3 members of your team sort of running around trying to plug things in, and you're like, quickly download it, reset the field, you do this, you do that, and you're sitting there on the field with your laptop's covered in scratches, which I'm sitting in front of my laptop right now, which has war scars from the days of when I did Vex. So yeah.
All right, well, I guess we should move on then to the Q&A. So does anyone have any questions at all for us? It could be related to this, it could be related to our experience. Anything you want us to add, or are we mostly all good? I'm going to take 20 seconds of silence as confirmation of that.
Meanwhile, I'll try and find this meme that I saw recently.
How do you stop Vex chain snapping on your intake against 8757C?
You don't use chain.
Okay. Well, I'm guessing we're good. I just wanted to add quickly, for some of you guys, was anyone planning on coming down to the scrim we had this weekend? It is the first in-person event in Victoria in a year and a half.
Yeah, I'll see you there, Spencer.
Oh yeah, you'll be coming? No, okay. Well, I don't think you guys will be coming because you're from NZ, but I know me and Sol are going. If any of you are interested, just message me on Discord or tag me and I can give you the information. But that's a great way to see all this hands-on, people with robots on fields, competing with each other, screaming as everything's going wrong last minute, uploading their code on the field. And we'll see all of that on Saturday. So if you guys do want to come and you are interested in learning more, that is something you can do.
Yeah, and for those of you new to Vex, welcome to getting half of your life just being suckered away. I'm sure you'll hopefully enjoy it.
That's pretty much all it is, isn't it?
Yeah,
Yeah.
yeah.
All right. Well, I wanted to thank you again, Lachlan, for coming and running this meeting. I really
Thank you very
appreciate it. Your
much.
knowledge is immense. You have taught me so much about Vex, and you've taught all these guys a lot about Vex as well. So thank you so much again.
My pleasure. This is like the fifth impromptu workshop I've run this week for like so many different topics, and getting very good at pulling these out of thin air at the last minute and trying to share the things that I know.
All right. Well, that's it for the meeting. Thanks again for coming. And if you're watching a recording of this on YouTube, if you have any additional questions, feel free to put them in the comments and we'll try and answer those. And yeah, thank you again. And that is the end of our meeting.